Let me show you the benefits of testing stuff before you make silly claims. Let's suggest that we're on an island in the middle of the Atlantic, nothing but water all around you for hundreds of miles. At any given time, you will have the ability to view 180 degrees of the sky, 360 degrees around you. Sure, it's actually a little bit more when you add in the horizon drop and refraction, but for this demonstration, we'll just keep it a clean 180 by 360. Fair? You will see that even without those minor adjustments, the results will be quite conclusive. To simulate this, I'll use an old 360 degree camera of mine. But I will limit its view to 180 degrees by using the super high-tech method of putting a bottle cap over one of the lenses. Then I test the field of view of the camera and mark the degrees, so I know what I'm looking at. Easy enough? Okay. What this gives me is a usable platform which I can simulate an entire sky in one single shot. And since I don't have an island in the middle of the Atlantic, we'll just have to settle with this parking lot in Kaiserslautern, Germany. Now all I need is some props for markers and to measure some scale distances, and we can judge what can be seen from the globe. Okay, so let me tell you what I have set up here. Many will remember this sphere that I used in Quickie 6 for the perspective test. The diameter is 19.6 centimeters. Round that up, and we'll make it 20 centimeters. Here's the stated diameter of the sun. So yes, using those numbers, we are also testing the globe model. So if I divide the stated diameter of the sun by the 20 centimeter ball, I get 69,635 kilometers per centimeter. And using that ratio, I can place my Venus and Mercury at proper scale distance to the Sun, simply by dividing the stated distance to each by that scale ratio. The last value needed, which I will explain in a moment, I need to mark that as well. And there's plenty of tools for doing this, so I'll just use this one to get me that value. Now I have my model, to the scale of the size of the Sun object used. Now, one thing needs to be made perfectly clear here. While the Sun size and the distances to all the objects are to scale, the diameter of Mercury and Venus are not. This test is only to judge what is potentially visible due to their location on a globe model, not what size the planets will be observed, because the unaided observer would just see them as bright dots in the sky. But it needs to be reminded that the flat Earth claim is that Mercury and Venus would never be visible without the Sun in the sky. This due to their inner orbits and flat earthers using often wildly out of scale drawings. So to flat earthers, the night observation of Mercury and Venus would be impossible. So now let's show field of view. As stated before, in the simplest conditions, a person can see 180 degrees above them and 360 degrees around them, which is often referred to as one half of the observer's celestial sphere. On a rotating Earth, when viewed directly above the North Pole, the field of view of an observer on the equator during the equinox would look like this. Of course, this extends out infinitely, but we'll use this half of the celestial sphere to make it easy to understand. Rotating around with the Earth, obviously the field of view moves with the observer. Now let's add the equinox sun, and now we'll rotate again. Here you will see that for half of the day, the observer would see the sun, and the other half not. At this point, the observer would experience sunrise as his horizon is starting to see the sun in the distance, and the sun remains visible until sunset. Even after sunset, the sky will remain illuminated from the sun, but grow increasingly dimmer as less of the atmosphere is illuminated directly by the sun, even though at this point, the observer can no longer see the sun directly. This is called twilight. Twilight occurs when the sun is below the horizon to the observer, and finally gives way to full night once the sun is about 18 degrees below the horizon. But when the sun is a mere 6 degrees below the horizon, it is dark enough outside for the intensity of Venus to be seen through the dim sky. So now let's go back to the model. Let's rotate the observer's field of view as if the Earth had rotated an additional 6 degrees. So the observer, rotating at the equator to a point where the sun is now 6 degrees below the horizon, this would be a time which in the sky, the light of Venus and Mercury should be potentially visible, and will continue to be visible as long as the tangent of the observer's horizon remains between the target and 6 degrees from the sun, and as such can be seen just fine from the globe. Y'all have a nice day.
Oh my god!